Lesson 12.1, the counting principle. So this is probability, and we're going to do a lot of real life situations where we're discussing what happens. For example, we're going to a restaurant, and there's a limited menu. You have nachos and wings, then you have chicken, steak, or fish for the main dish. The nachos and wings are appetizers. And then you got pie and ice cream for dessert. So, if you have nachos, you could also have steak, chicken, and fish. If you have steak, you could have pie or ice cream. Chicken, you could have pie or ice cream. Fish, you could have pie or ice cream. And then, of course, we have to repeat it all for the wings. Pie or ice cream, pie or ice cream, pie or ice cream. The question is, how many possible meals can we have? Well, let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 total. Now this is a tree diagram, and it looks complicated. It takes time, and it does. It's a great way to visualize things, though, and I'll do that a lot in probability. But it's just an application of the fundamental counting principle. We have 3 categories. If they are independent events, I can pick nachos and steak, nachos chicken, nachos fish. It doesn't matter what I pick. For an appetizer, I can have any meal I want. And some people would argue that it does in this case, but for now, we'll say it doesn't. Well, then we have 2 choices for appetizer, 3 for a meal, 2 for a dessert. Multiply them up, we get 12. That is the same answer we got up here. So that's how we figure things out. And I'll give you some examples. How many different area codes can we have in the United States? In this case, don't worry about any government restrictions. Well, an area code has 3 digits. We have 10 choices, the digits 0 through 9. Because a lot of people say 9. There's actually 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I can put 10 in each category. So we have 1,000 different area codes we could have. Now that's an independent event. Let's change it up a little bit here. We have 5 books. We want to put them on the bookshelf. So there's 5 slots. But this is a dependent event. We'll talk more about this in a minute. So I have 5 books to choose from. I put 1 here. So that was my 5 choices. Now we get rid of that book. We can't use it anymore. We've placed it in the first category. Now there's 4 to choose from. Then there's 3 to choose from, 2 to choose from, 1 to choose from, until there's no more books. Multiply it up, we get 120. The shorthand for this is called 5 factorial. That button is on your calculator. I'll show it to you another time. We call this multiplying a factorial. 5 factorial, like I just showed you, is 5 times 4 times 3 times 2 times 1. 7 factorial will be 7 times 6 times 5 times 4 times 1. So you can put them into your calculator, or you can just do them. 4 times 3 times 2 times 1. Do I really need to multiply the 1? No, of course not. 24. 2 factorial is just 2. 0 factorial is 1. More on that later. It has to be 1, otherwise we cannot do certain problems, and it causes all sorts of difficulties. 8 factorial is 40,320. Now, as always, life gets more complicated, so you're going to have to try this problem. I go to an amusement park. There's 9 different roller coasters. I want to go on all of them. I want to go on all 9. How many different ways can I do that? Well, if you look at the list, got 9 to go on. I got 9 choices. Now, I've already gone on that one, so I have 8 choices. Times 7, 9 factorial. I have 362,880 different ways to do it. That's a lot. But if you've ever been to Cedar Point, roller coaster capital of the world, and you want to go on them all, you better be young and you better be fit and you better get there early because they really fill up fast, especially the popular ones. So in this case, we're only going to go on 6 of them, but we still have 9 to choose from. And after we've used that one, we still have 8 to choose from. So now we only have 60,480 ways that we can do it. So we just set up the problem and look at it. Now, I'd like to say it's common sense, but it's common sense in the world of probability. You have to have seen stuff like this before. Otherwise, it's very challenging to put it together. So there's one more way to look at these problems, independent and dependent. We already talked about that. Independent, it's things like rolling dice. One die doesn't care what the other gets. Be things like picking the phone numbers. You can use any digit you want for the first, any digit you want for the second, so on and so on and so on. Now, what about dependent? That would be like picking names out of a hat. Once I pick a name, I can't pick it again. A lot of times they put this at the end of the problem. It seems kind of obvious to me, but it's good to be clear. Without replacement, meaning I picked a name out of a hat, I didn't put it back in. Why I would put it back in, I'm not sure. When I pull a name out of a hat, toss it out. That's a dependent event. No chance that I'll get that again. Pulling just a straight deck of cards, I pull out a 5 of clubs. Well, there's no chance I'll pull that again. That's a dependent event. That takes practice, so I've given you a bunch of problems. Good luck.